Alright, hell yeah. So 1 hour on the clock. So a subscriber, or a viewer, don't know which, but hell yeah. They gave me this problem to do. And you know what I mean? So if you want me to do a problem, you have to be very specific. Write the exact just write these first two sentences of a problem, and then I can find it on the internet. And someone already did this on YouTube, so you can look at the answer. They probably did it in 7 minutes. What we're going to do is do this probably in 3 parts. It's probably going to take me 3 hours to do. Who knows? But I'm only going to give this this part 1 just 1 hour. So I'm giving this this viewer 1 hour of my time. And so hell yeah, let's begin. So the first thing we need to do is read, and let's do it. So a block of mass m. So, okay, oh, hell yeah, this is, I didn't even, I was just kind of glancing at this problem. I thought maybe this was a circular block of, but anyway, so this is the block. All right, hell yeah. And then it has a circular cut right there, and a quarter circle is cut from it, with a frictionless surface. Okay, hell yeah. The block rests on a horizontal frictionless surface. Okay, booyah. You know what I mean? That and don't confuse. I mean, it's really difficult to visualize and mentalize a frictionless surface. They don't exist on Earth. Even like a very slippery ice surface, still, like you push a hockey puck, it goes pretty far, but then it slowly stops. So, you know what I mean? So we'll just have to extra visualize that. Okay, sweet. And the block rests on the horizontal frictionless surface of a fixed table. Cool. Initially, you know, I mean, if you're getting detailed, this problem happens on Earth, I would just imagine. You know what I mean? Hell yeah. So initially, the right edge of the block, so that's going to be the right edge, is at x is equal to 0 in a coordinate system fixed to the table. So we have a fixed axes to the table. That's going to be the x direction, positive, and then we'll probably have the positive y direction. With this, I'm sure the block isn't going to move in the positive y direction, but this little chunk of mass, we haven't gotten to that yet, will move in the y direction. Sweet. So a point mass, okay, hell yeah. And even though they drew it kind of as a three-dimensional circle, we have to visualize this mass being, you know, just right along that curve. You know what I mean? It doesn't have a center of mass and a radius. You know, the center of mass is always just right in the same position of that curve. Cool. So a point mass m is released from rest at the topmost point of the path as shown, and it slides down. When the mass loses contact with the block, right there, and it's difficult to see from these drawings, but right there you have a perfectly horizontal surface. I mean, you're going to be sloped in, but then right at the lip, that's a horizontal. You know, if this is dx and you know what I mean, that gets incrementally small, we're going to have a horizontal surface. So that point mass is only going to have a velocity in the x direction. Velocity in the y direction will be 0, and velocity, its actual just velocity will just be v of x. Sweet. Cool. So when that mass loses contact with the block, its position is x. Okay, hell yeah. And its velocity is v. Okay, so we were just kind of talking about that. At that instant, which of the following options is or are correct? And so we better read these, you know what I mean? Because else we don't, I mean, I'm sure what we want to find is like, what's the velocity of the block? You know what I mean? Because even as this thing gets to the halfway point, this block is going to start to move that way. The only location that this block remains stationary is right at the top of that arc. The same thing is going to go on where this point mass is just dropping vertical for like a split second, but not really, because even at the top, that curve, even if it moves any distance this way, we still move a distance that way. We can consider it negligible, and so And so what does that bring up? It means that from there to there, it's like the ball is just falling vertical. It does pick up speed, for that split second. But what it doesn't do is move from here, and I'm going to call this like x prime is equal to 0. You know what I mean? So I don't know if that's going to be confusing. Well, we could just say this is x is equal to negative r. Cool, so let's do that. So when x is equal to negative r, and we drop this mass for a very short distance, technically it does move slightly. All right, we're about 6 minutes in. Pretty sweet. Okay, so, but let's just say for this tiny distance, like right there to right there, because we just need to kind of visualize what's happening with the problem. This mass is just moving in the vertical direction. We're going to say this direction, it does not move in that direction. Okay, hell yeah. And so, and in that case, from there to there, it's like this block doesn't even exist. You could say that. I mean, it's just like, who cares? Because this is a frictionless surface. This is even though this point mass is resting up against a surface, that surface is frictionless. And it's as if, we just took this point mass and dropped it from there to there. And that's a perfect representation of what's happening to that point mass, where you don't need a block, you don't need anything else, so nothing else is going. And I think that's useful, because it's just a bummer that they actually don't start this block. If it had a flat spot, and if it actually started up here, we could say that's 100% going on. If the block started up here, and we just drop it to right there, there's like literally no interaction with this big mass, this block of mass m, that is a frictionless slope, that's on a frictionless surface. Okay, so now we're in the real world where, this so this point mass is going to drop from there to there, and what happens is we have a slight curve, near the tangents, like for look at this, even just visually. If I drop all the way down to here, hey, I went pretty far this direction. It looks like I went radius divided by 2. That would be the diameter divided by 4. But look at this direction. The point mass just moved in the x direction from there to there, not very far. And so let's quantify that actually. You know what I mean? If this is half the radius, this is a quarter of the radius, and sure. Well, it doesn't even look like a quarter, but we're going to call that a quarter. So we're going to say when this particle moves a vertical distance of r divided by 2, it's going to, yeah, my bad. This is r divided by 4. This is the radius, and we divvied it up 4 times, and we see that one of those distances looks kind of close. It almost looks like a fifth, but who cares? Okay, so hell yeah. And this is the radius, and so we're going to say when this particle drops half the radius, it moves in the x direction. Because we were saying that if the particle is just up here on a flat surface, and it just moves in the y direction, you can just get rid of all other aspects of the experiment. But because this particle moved that quarter distance, let's talk about that. And let's say, instead of this curve being like a circular curve, we're going to say from this radius divided by 2, that's this distance right here, and then this radius divided by 4, we're going to simplify. We're going to do the first simplification of this problem, and we're going to say that is a wedge shape, and it's just like that. All right, hell yeah. All right, so we're going to take a pause on this, and let's actually read these. Okay, so it says the x component of displacement of the center of mass of the block, we're just going to say, hey, the center of mass, well, you know what I mean. Let's say the center of mass is right there of the block. So the x component of its displacement, meaning that if it gets moved this way, that's positive. But if this particle is kind of, you'd almost treat it like a wedge. Because it's being pushed down by gravity, it is applying a force in that direction. And we need to even talk about that. Because if I have a particle of mass that is just going this way with a velocity, it wants to go that way. Literally, the only way to get it from here to over here is to put a force on it in this direction. And you're going to have to do that over a period of time. So if you do put a force, if you put this force right there, and move it in from here to there, and let's talk about this, because this is very useful to throw a time component. If you throw a time component on this of 1 second, then this mass moves from here to here, and we're just going to call this d. So it moves a distance d in 1 second. Okay, and so, but we have to be very careful about this. That's going to be, we can figure its average velocity is, and what's velocity? Its units are meters per second. So what's the distance that we traveled, and what's the time it took? The distance that we traveled was d, and we did it in 1 second. So our velocity is d meters per second. Okay, hell yeah. But just, let's say this is like time 0. We're going to say we just applied the force right at time 0. So you can say there's no force on it at this time, and then at this time, booyah, there's a force. So you have to kind of think about, you know, especially if you're going to instantaneously apply a force, and you can do this. There's some things that you can't do instantaneous. You can't change velocity instantaneously, I don't think. I think an instantaneous change in velocity would require an infinite amount of force. So we don't want to go down that rabbit hole, but just know that, hey, this mass did not have, I mean, it's just traveling across the universe with a fixed velocity, and it doesn't have a force on it in that direction. And then at this time, we're going to say time 0, booyah. We instantaneously apply a force. Now, prior to that, I'm going to ask the question, what is this velocity this way? So the velocity in the x direction is 0. So right before we apply the force, the same thing. Velocity in the x direction of this particle is 0. Now we're going to apply the force. At that very instant, what is the velocity? It is still 0. Cool. We apply a force on a mass, we do get to use Newton's equation, F equals ma. Alright, so this equation says that if we apply a force on a mass, we get an acceleration. So let's rearrange this equation. The acceleration that we would see is the force, the amount, the number on the force that we apply divided by the mass. And what is acceleration? This is the change in the velocity of the particle, like for change in time, and that can be change in velocity per 1 second. You know what I mean? Just to throw I always kind of like to do that. You know what I mean? What's my change in velocity in 1 second? Run the experiment for 1 second, and so that's what we did. We said visually in 1 second, this particle went that distance d, and so its average velocity in that x direction was, you know what I mean, that distance in 1 second, d meters per second. But we have 0 velocity here. So if I have 0 velocity to start with, or what does this equation say? It says if we do apply a force, we are and in this we're going to apply a constant force. If I apply a constant force, and that's what we're going to have in this problem, the force involved is going to be gravity. We have a mass, and we have, I'll write it up here, we have a force of gravity. And that force of gravity is going to be equal to the quantity of that mass times the gravitational constant, or the acceleration of gravity. F equals ma, acceleration of gravity, times the mass. That is the force being applied down. That's going to be a constant, even though, and I you know, one of my things is that if I ever write this, I am going to write Newton's gravitational equation, which is the gravitational constant, the mass that we're dealing with, the mass of the Earth divided by the radius of the Earth squared. It just happens that these three things don't really change. The mass of the Earth ain't changing. Gravitational constant by definition is a constant. The radius, and this typically gets, I shouldn't write radius of the Earth. I should just say x squared or just radius squared. But that's going to be from, here's the Earth, and then here's our little point particle on our little block right there. So the distance from the center of the Earth to the center of that particle, well, it just happens from sea level to wherever that particle. That distance is so meaningless that the distance can just be averaged. That is just the radius of the Earth. So that's the distance, and we do have to square that distance. All right, hell yeah. And those three terms just add up to g, which is approximately 10 meters per second squared. You can use 9.81. Hell yeah. All right, hell yeah. I don't know why I'm having a hard time kind of doing this proof, but you know what I mean. I think we're good because we know that there's going to be a constant force. Well, and in our problem, the force isn't going to be constant. The force is only constant as if you do have a ramp. If I have a particle that I'm just going to represent. All right, hell yeah, get some more ice water. So if I have a particle that I'm just going to represent as a mass, we're going to have a force directed straight down. So it's going to be the force of gravity. Now, you know, from observation, and let's say this is fixed. This triangle we're going to fix, just to make a simpler problem. The path that this particle is going to take is this direction. And so the particle can't go into the ramp. You know what I mean? So we kind of have two orthogonal directions. One, the particle can never sink into the ramp. You know what I mean? Just like if we're on the surface of the Earth, you know what I mean? We have a force on us, but we're not sinking into the Earth. So in that case, the Earth is pushing back with the same force. Force of gravity is the normal force that we're experiencing. Those are equal. But in this case, in this case, our velocity is 0. You know what I mean? But when we run this experiment, I always like to do eyeballs because you can set this up and you can have this mass at rest and then let it go. And what you're going to see is if this is a frictionless surface, this mass is going to travel down there, and then it's probably going to, well, one, if it starts to travel, we know we have a change in velocity. That's a check on reality that if I did this experiment and this mass had 0 velocity, I let it go, that's the definition of acceleration. Our velocity went from 0 to some number, so it changed, and we have a change in velocity, and this is you know what I mean, this is classical physics where that change in velocity cannot happen instantaneously in a classical physics perspective. So we have some sort of change in time that's associated with that change in velocity, and those two terms we can get a value for acceleration. That's the definition of acceleration. The acceleration as a point is where this change in t approaches 0, so that's the limit as change in t approaches 0. And I swear to God, even last month I would not write the limit of, you know what I mean? But I guess I'm kind of getting the hang of the calculus. Anyway, and I kind of understand that from that perspective now. Cool. So this thing is going to accelerate in this direction, but it can't go in the normal direction. And so what we have is that only the component, we're gonna take this force component and then divvy it up into two directions, this way and this way. And anytime you have a force component, just know, and then let's say here's the angle of the ramp, just know that you can chop it up. Let's do this just a slightly bit bigger. And this is going to be our ramp angle. Just know that you can take this force component and use the parallelogram addition of components. So to get from here to here, I can go two different directions. I can go down the path and then perpendicular, or I can go perpendicular and then down the path. So this main vector is the force of gravity. This is the component down the ramp. This is the component into the ramp. So this would be like, this one would be the quote-unquote weight, as if you had a constant scale, or if this ramp was just a scale. You know what I mean? If this ramp was just a scale with a block of mass sliding down it, the scale would have a readout of that weight. And that weight would remain the same even if it's changing velocity in this direction. The reason this weight stays the same is because we don't have any change in velocity in this direction. So we have the sum of the forces. We're going to call this the y prime direction x prime. The sum of the forces in the y prime direction have to be 0. We have that component of the force of gravity normal to that surface, and you know what I mean? And since we do have a component of the gravity in this direction y prime, like, hey, if that's the only force that we had, you know what I mean? Hey, you need to, just like on Earth, if I have Earth and I'm a chunk of mass and I know there's a force on me, hey, there's a chance that I might, you know, sink all the way to the center of the Earth. The only way for me not to sink to the center of the Earth is at all times if there's a constant force balancing me. One, I would have to start with 0 velocity, and I would have to have a constant force that balances. We're going to call it the normal force. That is a very good explanation, and I love things that make you feel claustrophobic, where you're just like, damn, I hope the normal force is always there to make me not sink to the center of the Earth. That would suck. Alright, hell yeah. So what we need to do is we need to get this problem to... oh yeah, what is the deal with this? Because I said that we're just going to have a force in that direction. And I guess we do. Maybe there's more going on here than meets the eye. Because... and I just said the weight was going to be equal to the weight of it. But maybe that's not true. I don't know. Like, I'm kind of losing my mind now, because I was trying to come up with a scenario where we have a constant force in that direction, and I thought if a point mass was sliding down a linear ramp, then that would be a constant force. But maybe that's not. Maybe that is not the case, because I don't know. Yeah, do I need to take my first break? We'll bust out a card. Yeah, let's think this one. This is kind of the first place that I'm kind of stuck. Let's say this particle takes 1 second to get to there. You know, so that's kind of similar to what we got going on there. And this is just a distance d. So again, we have no velocity this way, and then we have velocity this way. To finish this part, if I find a way to have a constant force sideways, that's the only thing. I don't know if I have a constant force sideways. I'm sure I don't. I'm sure this force in this direction is always changing because we have a circle here. And even on a ramp like this, it seems like the force that way is constant, but like, why am I having a hard time with that? Well, let's talk about driving. I always talk about driving forces. So, I mean, because if we don't have an Earth underneath us, and this thing's mass and I don't know. Yeah, and let's say this is massless. So we have, this is just an experiment floating in space. This is a chunk of mass, and then we put a massless foam ramp next to it. Nothing's going to happen. You know what I mean? This point particle of mass, unless some force acts on it, is just going to chill right there. I think that's one of Newton's laws, that if you got two chunks of mass just hanging out, and they're both going the same speed or no speed at all, they're just going to be in that same position at time is equal to 0, at time is equal to infinity. Until a force acts upon those things, nothing's going to happen. And so that's why I kind of use this idea of driving force. So we do have a driving force, and we are going to fix this ramp to a table. And we're going to say the driving force is gravity. Gravity is acting in this direction, and we don't have any frictional force. The force of friction will be 0 because this is going to be a slippery, frictionless ramp. Now, and then let's make it even a simpler scenario. What if I just dropped this mass right here? Well, we kind of know what's going to go on with it because there's nothing to resist, and we have a force of gravity. So that's the simplest thing we can do. We can say that Newton found a relationship that if we observe a mass and we apply a force on it, this equation holds. That the force is equal to that mass times the acceleration, or we can say the acceleration of that mass is the force applied divided by the mass itself. So if we increase the force, we're going to increase the acceleration. If we apply a constant force and we increase the mass, the acceleration goes down. Both of those would be linearly proportional. Increase one, double one, you doubled acceleration. Double this one, you half the acceleration. So one would be linear inverse, the linear inverse. Cool. So, and then with ramps, I think it's very useful to be like, let's do a ramp like this. Because sometimes it's not obvious. You're just like, well, if I drop this, it's going to take a certain amount of time to splat. And then what if I drop this? Is it going to take the same amount of time? That's something that I might forget. And so what I always do is just go to a icy slope, a frictionless, like a air hockey table. I've done this with lifting an air hockey table and sliding a puck across it. If your ramp has a shallow angle, hell, it's going to take a lot more time to get to the bottom here than just dropping it. And in this case, it's going to take way more time than in this case, whatever time it took. This case will be bigger than this. This will be much, much bigger than the time it takes to slide down that ramp. Cool. All right, so now let's prove that there's a constant force in that direction. And how do we do that? Well, we say that we have a downward force. And let's see. Oh, on this ramp, even if we just start right here, we do have a downward force of gravity. But the only thing that we can do is to try to balance it with a normal force. And that normal force is going to be in a perpendicular direction. So we can this is where you need some trigonometry skills. Because if this is theta, the angle of the ramp, this is going to be phi. And then, so let's just start drawing. And this is, and then to make it simple, I use this acronym. If this is theta and this is phi, but I have really small triangles, I'm going to do theta as an angle and then phi as a dot. So it's still representing that angle. And these are just complementary. Theta plus phi is equal to 90. Theta plus phi is equal to 90. So even though my triangles are going to get really small, I can still use that. So hell yeah. So I'm going to use the Zorro method right there to find that that's theta. So sorry about this angle. This angle was phi. So let's do that. That angle is phi. My bad. And you can see the other thing is if you have 180, like I know this is a 90. So if I come in with a 90-degree corner and I'm saying this is theta, then this has to be phi. There you go. So and if so if I have a 90 and that's the 90, this will be theta, this will be phi. So that's kind of my little acronym, you know, just so I can actually see these angles. And then I'm going to draw a line of action right here. And so let's get some more juice. Alright, hell yeah. So we're back. And, you know, this is a steep angle, so this should be fairly shallow. I kind of probably messed it up. But, hell yeah. So this is phi, theta. And I can see that this is a 90. So I have theta and phi. This is a 90. So I have, so right here I have theta and phi. And those add up to a 90. Right here, here's a 90. If this is phi up here, this is theta. And then this is phi, and then that's theta. So I could probably redraw this. And we'll see if I do. Get another sheets of paper at the ready. Yeah, so let's redraw this. So here's our steep angle. We're trying to represent kind of the top portion. We're going to have our most, we're going to have our least change in angle, change in distance that way, d. So, you know, we're still trying to solve this one. Hell yeah. So we have theta, phi, messing up right off the get-go. Hell yeah. So we're going to have our normals, and I'm just going to, you know what I mean, draw a horizontal perpendicular, and then draw perpendicular to the slope. And now we can just see how this is a triangle. And I'll try to do as many phis as I can. So we'll do that. This is theta. If this is 90, this is phi. If this is phi, this is theta. This is phi. If this is theta, this has to be 90. This has to be 90. So this has to be theta. Cool. This is 90. So this has to be phi. This is 90. So this has to be theta. I don't know. I think that's just a good practice to do. And then we have a downward component of the force of gravity. That's going to have two components. One is going to be in the direction of the normal force, and then the other will be in the direction of the ramp. So we're going to have Fg, and I'm going to say that the rotated axis is y prime, x prime. You know what I mean? So now we have, and I don't know if I should have done that. I should have probably said this is the y direction. And, yeah, because this was, let's see. This was the x direction, and this was the y direction. And how are we rotating this? We're rotating this way. So we're going to have, I don't like that either, but sure, this is y prime, and then this is the x prime direction. That makes more sense. And we are actually rotating this a phi, even though this angle is theta. But we're taking our vertical ramp and then rotating it out phi, and then the face of this, you know, from material mechanics, that's kind of what they do. They say, hey, this angle, like the normal, this x is now rotated up to an x prime, and this phi is rotated the same as that phi. Cool, and you can do that from just taking a chunk of 90-degree paper. When I take this and then I rotate it out to this angle, like just focus on this line. What happens to this line? So we're going to say this line was right here, and now when I rotate it out to this angle, we're going to draw that line, and we're going to find that I don't know how to draw this, but you know what I mean. There's our angle, and we can see that that matches the angle that we just rolled out. Alright, hell yeah. I don't know why this is so brutal for me. I think it's just because I have to do like every step just to feel like I can move on to the next step. I have absolutely no idea. But yeah, what do we got going on here? Is that we have that chunk of mass, we have the force of gravity down. The only thing that can resist it is a... and we know from observation that this thing is not going into the ramp. So therefore, this normal force, the normal force in the x prime direction, so if we do sum of the forces in the x prime direction, we're going to have this is equal to 0. We're going to have the normal force in the positive x prime direction, and then we're going to have a minus the force of gravity. And the component of it will be this component. So if we use theta, I think we should use phi, and I'll now say it's phi. It's not phi. It's called phi. But anyway, here's phi, and so that's going to be the sine of phi. So we're going to have Fg sine phi. Cool. So that's going to equal 0. So the normal force is going to be Fg sine phi. I know what the angle of this ramp is, and I know the force of gravity on this, because I know the force of gravity is just the mass of that particle, the gravitation constant, the acceleration of gravity, and then sine phi. And again, force of gravity, gravitational constant, mass of the Earth, radius of the Earth squared. These three things are just equal to g. So force of gravity is mass times g. All right, sweet. So there you go. And but now we have an unobstructed force. So if we do the sum of the forces in the y direction, they are not equal 0. Dynamics say the sum of the forces in the y direction are equal to the mass times the sum of the accelerations in the y direction. I think the summation is on both those. I think these are both vectors, you know, that you actually use the summation sign. Okay, but we only have one force. That's why and I kind of forget. It's just like, are some things acceleration by observation? Or does every acceleration have an associated force? I kind of forget that aspect. It would seem that this equation would say so. Alright, but let's just keep it simple for this one. We do have a force, and that's going to be Fg cosine phi, which is going to be mg cosine phi. So we have a force, so we have a negative, and that's going to be in the negative y prime direction. So we have a negative mg cosine phi, and that's going to equal the mass times the acceleration in that direction. And so we have the acceleration in the y prime direction. Cool. And masses cancel, and so now we know the acceleration in the y prime direction. Alright, hell yeah. I think the thing that's tripping me out, and that the light bulb went on, is that this force is always the same in this perpendicular direction. We used Newton's laws that says, hey, our velocity in the x prime direction of this particle of mass is 0. It always is when our ramp is linear. But we do have a force in that direction. I mean, the downward force due to gravity still has a component that wants to move it. You know what I mean? Just like, hey, we have a force that wants to sink us to the bottom of the Earth. But we're not. By observation, this block is not moving through the ramp. So there must be an equal and opposite force to balance the component that actually wants to sink it through the ramp. It just happens that that component's always going to be, the same as we go down this ramp that's linear. But that's not going to be the case when we go down this ramp that's always changing. So, but we did find from this that at any given point where you have, let's say this is just a blown up, let's say this is a portion of the ramp, and we just have this section of the ramp, and we'll call it a ds, because this would be the arc length of the ramp, where ds is approaching infinity. Hey, this is a linear portion, and what we can see from this is that we know what the normal force. See, now I'm kind of slipping again, but yeah, at any given ramp angle, we know what the force of that particle is in the normal direction. So here is where my light bulb went on the second time, is what we can play around. So yeah, it's still confusing that, like, hey, we're having this this particle of mass, we have a force that way, and then a balancing force that way. Oh, I kind of lost it. I was going to change the angle of the ramp and come to a conclusion. Alright, this is harder than it looks for me, but I think I came to the conclusion that I wanted to come to. What I want to do is simulate this. So I have this ramp, and then we have this going on. What if I change the angle of the ramp, you know, kind of just all of the sudden, just kind of like this, and we're going to do two things. I'm going to say that these distances are kind of small, but what we're looking at is, and this is, we're going to do perpendicular distance, and we're going to say that this distance right here is the same as that distance, proportionally, and this angle is really small, this change in angle, and we can just call it d theta. Alright, hell yeah. So I think I'm onto something. I'm trying to, you know what I mean, I'm trying to derive this from like just a tangible perspective where you can kind of just get it. Because what did we say? We said that there is going to be a component, and so I'm just going to say there is and we're going to call this mg sine phi. So that is the component, and we're going to say this is phi. And then that's going to be the component of the gravity normal. And then we have a normal and these are equal because this particle is not sinking into the ramp, it's not levitating from this, and this was the y prime direction. But if we instantaneously change the angle of the ramp, which we will do on a curved surface, then this is going to be y double prime. This was x prime. And then so right here, the tangent to this line is going to be this. So this is x double prime. And then this is also d theta. But the same principles apply. You know what I mean? The downward component, we're going to still just have a force of gravity into this steeper ramp. So that's what we have going on right here. That's going to be mg sine phi, and then it's going to be probably minus, because this angle, the ramp angle gets smaller. The ramp angle used to be steep. Oh, no. We're doing a scenario where the ramp angle gets shallower. And so this new ramp angle is going to be to here. And that's going to be a shallower angle. So this is going to be phi plus d theta. I should just say d phi. Sorry about that. So this is d phi. This is d phi. So we have phi plus d phi. The change in the angle. So here's our angle, and it's phi. So we have angle phi. We have the change in phi. And I wish I just used theta. I think it's easier for me to say. But hell yeah, we did it. So, and then this normal force increases. It's going to be mg sine of phi plus d phi. And the sine of an increasing angle from 0 to 90 gives a bigger number, and so we get a bigger. But that normal force is still the same. It's just n prime, or I would say this is n prime, this is n double prime. And those are still equal and opposite, because even on this steeper ramp, this particle is still not going into the ramp. But then what happens? Because we said that the particle was going down this steeper ramp, chilling, doing its thing, and then all of a sudden, and then this is where we bring in this idea that in this x prime direction, this thing has zero velocity in the x prime direction. It doesn't have any velocity that way. But the second we change the angle of this ramp, what we do is at this point, that's where, like, hey, we're talking about like the I don't know, like oh yeah, so that's where you do yeah, from the dynamics equation, force is equal to mass times acceleration. Like, you might observe acceleration and then there isn't a force associated with that acceleration. Yeah, that's kind of fascinating, because that's what we have. Like right here, at this point of the change in ramp, our velocity in the x prime direction is still 0. And yeah, so let's, yeah, because this is the y prime direction, and what we're trying to say is this x prime direction right here. This is the distance that we'll be traveling. Our velocity is still 0 in this x prime direction, but how do we get this particle to here? Well, and let's say this took 1 second. So that's very similar to what we have over here. So this takes 1 second, and we travel a distance d, and so we have an average velocity of d meters per second. We have 0 speed here, and we're going to say because this distance is so, like this 1 second, we're just going to say is a very negligible time. You could do 1,000th of a second. But we're going to say that this 1 second in the scheme of things is a very small snippet in time. And so we're going to assume a linear increase in velocity. So if we do have velocity in the x prime direction here equal to a value, we have 0 here. And so if we did a chart on this where this is time, and this is 0 and this is 1 second, and we want to know our velocity in the x prime direction where this is 0 and this is some value, what's going to happen is the area under this curve is the distance. So what is the integration is taking this value and multiplying it by that. I mean, the units on integration is like, hey, you have seconds here and you have meters per second. Integration says we're going to multiply those two together. It doesn't give you the value just by saying I'm going to multiply that number by that number. Hell no, because we were taking the area under the curve. It could be this number times this number. If it was a square, we got a rectangle, we got to half it. But just from the units on integration means, and the reason we're taking area, means that whatever this axis is, we're going to multiply it by the units on that axis. So seconds cancel, and we're going to get units of meters. So the integration of this is distance. And so, but to get a distance of d, I want a distance of d when I multiply this. And so this triangle is going to be 1 second times a number that has units of meters per second, which is meters per 1 second. The seconds are going to cancel. And that has to equal, oh, and because it's a triangle, we're going to have to do 1/2, and that has to equal d. And guess what? You know what I mean? We want to solve what this number was, get this 2 to the other side, and we can see that this value, sorry, this is just a roundabout way to say that the velocity is double here. 0 here, it has to be double to get an average velocity of, if this average velocity is 1 and we have 0 here, we have to have 2 there. So that's, and it gives us an average. And the average between two numbers is take this number plus this number, divide by 2. So we're going to have 2 divided by 2, that's going to be 1. If we have 0 plus d divided by 2, that's going to be d divided by 2. No, that is opposite of, these are velocities. 0 velocity and a velocity of 2. So if I have 0 plus 2d for my velocity divided by 2, that's going to give me an average velocity of d, and that's what we have. Sorry to mess that up right there. Okay, sweet. So this value is going to be 2d. That's going to be our velocity at that point. And then we can use the idea of the equation for acceleration. Acceleration is change in velocity, change in time. Well, we know our change in velocity now. Our change in velocity goes from 0 to 2d in 1 second. So we have 2d meters per second squared, or 2d in 1 second. You know, a lot of ways to write this, but our acceleration is 2 times that distance, meters per second squared. Hell yeah. And that is an acceleration. So it took some sort of force in that direction to do that. So that means that there is the force on this particle has to be in that direction, has to be in the x prime direction. And just from an intuition, the weight on that particle, or the normal force that this particle is going to feel on this n double prime ramp. So we're going to have, let's do that. So we're going to sum the forces in the x. We're going to be on this ramp, and we want to sum the forces in what direction? Oh, now I'm kind of confused. Do we want to sum them in... yeah, I'm tripping out because I got 2 different angles here, and I don't know. I don't know to use like right there or to use right here. So let me pause for a second. Oh no, okay, confusion over. So it doesn't. Yeah, we're gonna be on this shallower ramp, and well, yeah, and I guess we just have to say that this direction is going to be similar to x double prime, because we still want to sum the forces in the x double prime direction. So that's one aspect of this drawing that's not, it feels like not 100% what's happening, but as this angle approaches 0, these two angles are going to be the same. So as you take this experiment and say that this angle approaches 0, then these two axes are the same. And so, but we are going to say this x double prime, the sum of the forces is the mass times the acceleration in the x double prime. Or reverse, it doesn't really matter, because either way you split it, the force is due to the gravity. You know, we still have this as our new slope, but still this mass isn't dropping in, it's not sinking into the ramp. And so we still have the normal force. Oh, well, yeah, so that aspect, that aspect that this thing isn't sinking into the ramp is still there. But what we're going to have is it appears to be levitating because of this. It had to go up a distance d, and to do that, this normal force does increase, but you could think of it as like the original normal force had the ramp not changed angle, and that's going to be in the positive direction, minus the component mg sine phi plus d phi in the downward direction. So you know what I mean, a portion of this is going to balance. But because we do have this kind of levitation effect or an acceleration in that direction, we have mass. We are going to have a mass times acceleration in the x prime direction, and that's going to be a value that's equal to 2 times that distance. And so we do have a value on this. And so when we do this, like this isn't a statics problem. These two things don't equal 0. They have to equal this value, mass times that number. And so that's what we're going to find. So the normal force that we would expect is going to be the mass. Let me see if we get this right. So we have, this is our normal force. We have the force of gravity down. If we don't have any acceleration, these two cancel out. But if I just want to solve for the normal force, I guess I just add it to this side. It seemed like adding didn't seem right, but mg sine phi plus d phi. Cool. Alright, hell yeah. So we're almost done with part 1, but we have to, you know, kind of take it home with like, well, what's going on with this problem? So, you know, I'm just kind of trying to prove to myself that if we have a change in angle, because that's kind of what we proved, you know what I mean, and that's what this is. If we have this sliding down at a change in angle, and now I'm kind of, oh, this is fascinating. And because it wouldn't matter. You could set up this same problem where this is your ramp and it's on a frictionless surface. And so what happens is that you have conservation of the center of mass. So if everything is frictionless, it's the same thing as having this just floating in outer space and having this with a jetpack on it. And let's say to do this in outer space, what you really need is just a gigantic mass underneath that represents the Earth, because this table is connected to the Earth. This table is rigid, but you also have jetpacks on this that are, you know what I mean, just kind of firing at a constant velocity. So we just kind of have a constant velocity of the system this way. I mean, but yeah, so just when it comes to this frictionless surface here and then this mass getting driven down, and I think this is the case, you know what I mean, I would have to question myself, but the center of mass of this system, so the center of mass of a triangle, what is that, a third and a third? A third the distance and a third the distance, that's the center of a triangle. And this point, you know what I mean, if we found the center of mass of both of those, maybe it just migrates this direction. That center of mass doesn't change. So, well, maybe it doesn't change in the x direction only, because you know, what's going on here is that like obviously, you know, run the experiment. This this triangle ain't going nowhere, but this mass can be down there, and then so the center of mass in this direction hella did change. But the center of mass in the x direction stayed the same. So if this point was right there, that point is still like right there. You know what I mean? So if that point is like right there in our experiment, that point doesn't change, but this the big block of mass moves that way, the particle moves that way. And if this block is real heavy, it hardly moves at all, where this particle moves a hell of a lot. You know, this particle is all the way down here moving in the x direction, and in this block, and you could reverse it, where if this mass was way heavy, this is a very lightweight, you know, you could actually, you know, visualize that. So much mass that this thing just shoots out like a wedged dart. Alright, hell yeah. So now I'm going to kind of throw, you know, I'm going to try to get there faster. So gravity is 10, that's the acceleration, and we're going to say acceleration. In 10, if it's just dropping down, we can use the integration. So velocity would be 10 times t. The position would be 5t squared. And if we just drop it from here to here, our distance, vertical distance, is r. So we're going to have r is equal to 5t squared. We could say the time is r divided by 5 square root. And I was just wondering if we could have a time that it drops here. You know, if this just takes 1 second. Sometimes I like to do that. Just be like, well, what if that just takes 1 second? Does that make things just a little bit more tangible? What would have to be the case is if r was 5 meters, and that's always just gonna be the case for something that that falls like that. Cool. So, but that's when our acceleration is 10. But we know the acceleration of gravity. The acceleration of gravity in the vertical direction right here is 0, you know, because it's all being restored by that normal force. To where the acceleration of gravity right here is going to be 45 or 0.7. So, and then at 60 degrees, the acceleration of gravity is only going to be half, you know what I mean, because the component in this direction, due to the gravity, you know, using triangles is only going to be half. And so what I like to do is take a circle and be like, well, how much is a circle compared to the radius? It takes 6 radiuses to get around a circle. And so, so we have 6 radiuses for a full circle. We have a quarter circle that we're divvying up into 3 distinct sections. You know, so those are the arc lengths that we're going to use. So that's how I always try to derive this. It's just been a while. You know, instead of integrating the equation, just take 3 basic chunks and then sum them. Where we're going to say this is fairly vertical, and so if I said this arc length right here was 5 meters, well, it's going to take 1 second to go that distance. And then if I said the arc length right here, well, now I forget how I want to go about this. Oh yeah, you're using the force of gravity, which is it's kind of easy to be like, hey, it's dropping that distance. But what we're doing is taking a component and we're just saying we're moving in this tangential direction. So you could say like this first segment is like dropping a chunk of mass on Earth. This second segment is like dropping a chunk of mass on a smaller planet. And then maybe this third segment is like dropping a chunk of mass on the moon. You know what I mean? The gravity in that direction is just really slow. You know, it's like, even though that we're seeing it in like slide down a ramp, if you were just looking at it from this direction, a side view, you're just like, hey, it's taking that mass quite a while to slide down that ramp, but you're just looking at this angle, and so you're just seeing a mass go from there to there in a slower amount of time. And that's the equivalent of saying, hey, the gravity right here is only half, and we're moving in that direction. Actually, forget looking at this side view. It's if you're observing from the radius. So if you're observing right here, you're just seeing this move slower. So faster, so Earth, maybe, I don't know, Venus, and then, or Mercury, and then the moon. Those are the, you're witnessing, you're trying to look at this as a free fall. You're like, hey, free fall looks like you're falling on Earth, looks like you're free falling if I'm looking from this perspective on Mercury, and then it looks like you're free falling this perspective on the Moon. It's much slower. Yeah, so it's kind of an interesting way to go about it. So let's see if we can get the integration down. Holy hell. So what's the circumference is 6 times the radius. We got to divvy that up into, and so that's the arc length. That's the arc length of a full circle. And we're going to divvy that up into 12s. So we got to divide by 12. Sweet. So we just have 1/2 r. So these arc lengths are 1/2 of the radius. Oh, sweet. Didn't really realize that. So and now what? Well, we're going to use this equation for the Earth one. For the Mercury one, we're going to say it's 7. And then so velocity is 7t. And then position is 3.5 t squared. Which makes time position divided by 3.5 square root that. Okay, and then we would have half. So we would have... half of gravity. So we would have an acceleration of gravity of 5. Acceleration is 5. Velocity is 5t. Using integration, position is 2.5 t squared. All right, hell yeah. So I think I put in my hour. You know what I mean? Because I need some calories in me. But booyah. Because why I like to do this is because it explains what's going on from the Newtonian methods. And then it's just like, oh yeah, no duh. Like, you know what I mean? Energy says that whatever, like the energy of this, the velocity of this particle is going to be like the energy. So the energy initial right here is we have an mgh, we have potential energy. And then right here, if this is our datum, you know, we're transferring that all to kinetic energy, which is 1/2 mv squared. And so I could say that the velocity of that is 2gh, you know, square root that. So that is the velocity, you know what I mean? And so a lot of these, but you lose touch of, I hate going to energy first. I like to start with the Newtonian perspective of mass and forces on mass. And so... but we at least nailed that we have a center of mass of this block. Or no, we have a center of mass of the system. The center of mass of this particle compared to the center of mass of that block are going to be... that is not going to change. You know, as this slides down and you have forces... That's the same thing that happens when the Earth and a rocket gets blasted off the Earth. Is that the Earth moves that way and then the rocket moves that way. This rocket has a mass that's much, much smaller than the Earth. And then here's the mass of the Earth. So the mass of the Earth... that center of mass stays the same. So if the center of mass of the rocket and the Earth is right there, you know, it would be, yeah, it's just right there. If this rocket gets all the way up there, that means that the... this center of the Earth moved this direction, and I'm almost going to get this wrong, but the center of mass stays put. So the center of mass between those things stays the same. All right, hell yeah. So let's just kind of read these questions just for part 2. See if we could get there a little bit, or just kind of go down more productive paths. The x component of displacement of the center of mass of the block is this value. Okay, and we know it's going to be in that negative direction. Cool. so B, the position of the point mass is, you know what I mean? So, man, I feel like is negative. Like, so the position, so as this slides down and goes this way, like the block is traveling that way. I mean, yeah, so check this out. Let's say the center of mass just happens to be right there. And so is there any aspect of this that could change the sign? And yes, because we need an aspect that can change the sign. So if the well, no, these are both positive values. So let's try to come up with a scenario where we can prove this one wrong. Because if the center of mass is right there, you could create a system where the center of mass in this direction only, because the forces are gonna be okay with the center of mass changing in this direction. But in this direction, now is that true? The center of mass is going to change in this direction. I'll have to think about that one. But anyway, so hopefully we got this right. The center of mass just in this direction doesn't change. This block will move that way, this particle will move that way. So when if the center of mass is right there, or just along this axis, you know, somewhere along here, when this particle gets to this point, yeah, I don't know either. I'll have to kind of think about that. Just the fact that this is a kind of a three-dimensional object and this is a point mass, that's tripping me up. All right, so C, it says the velocity of the point mass. Oh yeah, so when it does leave, it's going to be this equation. So it's not just going to be 2gh r, or the height, so square root 2gh, which would be square root 2gr. We're going to have this as a multiple, or, you know, kind of a because this is traveling that direction. All right, hell yeah. And D, it says the velocity of the block M is going to be moving in the negative direction. Cool. And it's going to be some sort of proportion between the mass of this and then the mass of the block. And that would make sense. I could see that, because the only driving force is gravity on this block. And the only way to get this particle to move in directions that are in this direction, oh yeah, it's interesting, because I'll have to go back to seeing this. Like, if you have a flat ramp, like this still moves back, right? You know, it would seem so when we drop this, especially if this is frictionless. Yes, we got a couple things that are going on in my mind with this one from the intuitive perspective. But yeah, to have something go along a circular path, it requires a force to get it to go towards the radius. Because that's what I was exploring, you know what I mean, with this, and I think we did a pretty decent job kind of doing that a little bit. But yeah, it requires a force in that direction. The only way to apply a force in that direction is to... oh yeah, and that's the thing. Like, you know what I mean, if this particle needs to go in this direction, well, something has to put a force on it towards the radius. If you don't have something to put a force on it in the radius, well, guess what? The particle is just going to go this way. So you could think of this mass as being, you could think of this block being massless. If this block is massless and this mass goes to 0, then what that's going to mean is that this particle is going to land right there, and it's not even going to have any velocity in that direction. So hell yeah, we might be able to, yeah, so yeah, it's just fascinating. Like, was it worth it to go through like my process of solving problems? I have no idea. It's probably not tolerable to watch, but that's what we're doing. I'm trying to give this video an hour, and I haven't eaten. Blood sugar is low, but we just have a light bulb that went on, and I don't want to ruin it. Hell yeah, especially since this is multiple choice. If this block of mass is 0, so we're going to go through these, and we're going to put a 0 in each of them. What that's going to mean is that this chunk of mass is just going to fall right to the earth. And this thing is just going to slip right out, because it cannot provide any sort of resistive force. I think that's kind of interesting. You know, if you have this scenario, if this block has no mass, then it's just going to slide right out. And that means that the center of mass is right here, and the center of mass doesn't change. And so if this had no mass, and this is the center of mass of the system, sweet, cool. When this particle gets to here, this thing that has no mass is over here, as we would expect, because it doesn't have any mass. And then therefore the center of the system is still right there. So hell yeah, that is going to be the easiest way to explain this one, and I can probably maybe get closer to the right answer. So let's dive in. So that means that the x component of displacement of the center of mass of the block. So the x component of displacement. So we're just saying like the change in x. So we're going to find the center of mass, and then this value is going to be that displacement one way or the other. And so that should be 0 if this is 0. And guess what? It's not. It's going to be negative r. So this is not an answer. So I would say no on that one. Hell yeah, this is going to be super cool. Hopefully this works out. The position of the point mass, well, is going to be right there, which is negative r. You know what I mean? So when this mass is 0, this has to be negative r, and we're going to have m divided by m. So no, we have negative square root 2r. So that's wrong as well. So when this mass is 0, the position of the particle is negative r. And so that's wrong. Okay, hell yeah. And am I filming this? Because this is a golden moment of just like, you know, I do this method because at some point, you know, an intuitive, something's going to pop intuitively. And so hell yeah. So we have the velocity of the point mass. And even from Newtonian physics, the only way to get this mass to move that way, if it does have mass, is to put a force on it. The only driving force on this problem is the force of gravity. But then you have components that are going to be normal and then down the ramp. And because of that, you are going to have yeah. Oh, and then you have that aspect of that angle changing. And it's just like, I can't wrap my mind around that intuitively, so we're just doing the simplest. Okay, so the velocity of the point mass would have to be the velocity of the point mass. Now, that's a tricky one, because the velocity of the point mass, like here, is going to be, they should say the velocity of the point mass leaving the ramp. Well, and then they assume so, you know what I mean? They do not assume that this is 0, and that's kind of the best trick for this problem. So when this velocity gets to there, hell yeah, it's going to be the square root 2 gr. And so if this mass is 0, well, now we come up with a conundrum because we have a divide by 0. And so that would make this blow up. But no, this still works, because even though the mass can't be 0 in this, it could be hella tiny compared to this mass. And so if that's the case, this number could blow up. If m is significantly bigger than m, this bottom part blows up, which makes the velocity 0. So that's also can't happen, because you still would have the velocity of this be the square root of 2gr. Okay, hell yeah. So the velocity of the block, well, and then this is going to be a tricky one, because if this mass is 0, any force, if you apply a force on a mass that has 0 force on a mass that has 0 mass, F equals ma, says the acceleration, or the change in velocity, change in time, would be F divided by m. And if the mass is 0, this force, this acceleration goes to infinity. So that's what we should see, at least, is that if I throw in a 0 here, this equation goes to infinity, and it does. So I'm going to say D is the answer. The velocity of the block M is V. And so there you go. So at least we have a conclusion. And that was, you know what I mean? I wouldn't bet my life at all on that answer. But we put in a good effort, and it was definitely more than an hour, and I'm hungry as. So, booyah. So if you have other problems that you want me to try, you know what I mean? I'm going to go through the same nonsense of just starting from the basics. But for this one, hell yeah, you know what I mean? Then we used that and came to some conclusions that were pretty decent. So with that, thanks for joining me. Booyah.